Good afternoon, 8th and ninth grade science class. I am ready for page 332 to 336. And I so bad wanted to put this with the other day's lesson, your last lesson, but it was just too much. I couldn't get it all on, and I decided that I will make 2 lessons out of it. So it's not a big lesson, it's pretty easy. So I encourage you that when you get this lesson done, start on your study guide. That will give you, the study guide takes longer, it's a big lesson. So do part of your study guide today. Do the first 5 problems. In today's lesson, I'm going to back up and do just a little bit of review. It will make radioactivity decay clearer if we back up and do this little review. So we're looking at the atom. And we talked about how the center you have the nucleus, and that's your protons and neutrons. Your protons are positive, and your neutrons are neutral. That's how they got their name. They're neutral, and they're just tightly woven right here in the middle. Now, out around you have your electrons. Your electrons are negative charge, and so the protons and the electrons will attract to each other. Negative and positive, they pull together. Now we talked about the isotopes. Isotopes is when there is a different number of neutrons from the protons. So we call this not a stable atom or an element. If you put a whole bunch of them together, you have an element. So they don't have a stable nucleus. Now just for review again here, I'm just repeating myself, but you need to know this information. You need to be familiar with the atom. When I say neutrons, you know, oh, right away you get a picture in your mind. Or if I say electrons, boom, got it. Or if I say beta decay, or if I say particle decay, you should at least have some concept of what's happening. So if you look in your books, turn back to page, where was that experiment? On 328. On page 328, you have the alpha decay and the beta decay. And in today's radioactivity decay is connected to that. So when you have an improper balance of neutrons, they're not the same as the protons. An improper balance, then is when the radioactivity decay happens. And you would know a little bit about this in real life. It's when you mix 2 chemicals together of certain kinds and you get a reaction. Okay? The atomic bomb is a reaction of atoms. You put these together, you have a reaction. But this is in a huge scale in comparison to what we're talking about of 1 atom. Okay? When you have this decay, we talked about when they shoot that bullet out on beta decay, he shoots that 1 neutron out and he destroys other atoms when he goes. He's just like a little bullet shooting out through there and blowing apart other atoms. You have what they call half-life. Now this is today's lesson. Half-life you will find on page 332. Half-life is the time it takes for half the original sample of radioactivity isotopes to decay. Okay, whenever you have the radioactivity decay, it's destroying at a certain rate. So the way half-life works is that let's say it takes 100 years. It takes 100 years for half. Am I getting off the board? No, for half. So, okay, so we start out here, let's say we have so many pounds. I'll just say we have a certain chemical, it's an imbalanced chemical. And so we have, let's say we have 50 pounds. And I'm going to do English measurements. I think he used another measurement. This is a big amount. And 50 pounds of this chemical, whatever it is, it's decaying in 100 years half-life. So in 100 years from now, this 50 pounds will be half, 25. Got it? You only have 25 pounds. In 100 years from now, it won't be all gone, okay? In 100 years from now, the last half won't disappear, only half of it will disappear. So 100 years from now, you start out with 50 pounds, you go down to 25 pounds, and then you're half again. So that makes you 12.5 pounds left. Okay? So the second 100 years, you again lost half, because this is what we call half-life. You have 12.5. Oh, you can't see that on the screen, can you? Okay, I'll let you back up here. 12.5 in the second 100 years. Guess what? You're not going to live this long, and I'm not either, but if you would add another 100 years, which would be like 300 years, you still wouldn't be finished. You see, it's half-life, so it would be half of 12.5 would be 6, 25, 6 and 1/4. Okay? So now we're 300 years down the road, we still have 6.25. Now it's getting smaller, okay? Let's do another 100 years, and there you have 3 and 1/8. I can do the fraction better than I can the other one. And you see, every 100 years, it only cuts in half. Now, if you look on your book, in your picture there, he gives you a picture of the decay of 14C. And it's, for 14C, it's 5,700 years is half-life. Half-life for 14C, this calcium, is 5,700 years. It's cut in half. And so then you want to get it in half again, you have to go another 5,700 years. It's huge. And you also should look on turn your book over to page 334. I found it interesting when he's talking about different chemicals have different rates of half-life. And he's talking about it in the last paragraph of 334 before on your own. He says that it's pretty long, that C14 is 5,700 years. That's pretty long, he said. Excuse me. He said it would take more than 50,000 years for most samples of C to decay away. There are others even longer, however. The half-life of 238U, you can go back on your chart, periodical chart, and look of your chemicals, is 4.5 billion. Do you get that? 4.5 billion is half-life. Well, in my way of understanding years and millions and billions, oh, I could never see it decay. But it is. Slowly. It eventually loses its radioactivity, though, the longer it goes. Now, you can answer your other question there, 13.10, and I will talk about radioactivity dating. And if you see that there are no questions on there and you say this is not important, and you just slam your book shut and you say I'm done, if I would be there I would shake you. That's not true. Radioactivity dating is not like boys and girls dating, okay? This is dates 2020. Okay? Because of half-life, when something dies, then it will have the amount of, and they use specifically 14C as a date, and so you can check it and see how much is gone, or how it has shrank. And it has, whatever it has, the atmosphere around it has, that's what it has at life. But as soon as it starts dying, as soon as it dies, it starts decaying. And so, it's 5,700 years, C14. I didn't put that up there. He talked about it in the book. 5,700 years is half-life. So they use that to test rocks and to test things in the earth. and they say, oh, we know it's decaying at 5,700 years, so we use that to date when it was first created and when it was first made, and then it started decaying from there. Well, the problem of this is there's lots of problems with this type of dating. It makes the Earth go on and on and on and on and on. See, if we use that 238U, it would take billions of years. And so for the evolutionists, for those people, they love this dating. They love the radioactivity dating. So they keep using that there to say the Earth is millions of years old. Okay, there is a huge problem with that. Now, and it's not, okay, the Earth is not that. But now see what happens is, what causes this confusion, we can use this radioactivity dating in short terms. We can use it for the last 100 years or the last 200 years on a tree that died or something like that, and you can check it and you can tell it's accurate. But when you try to apply it to things that are old, it's not proven to be accurate. It varies depending on the atmosphere at certain times will make it more or less decaying. While we say that it takes so many years for something to decay, that's an average. It's not exact. And so depending on the atmosphere around it, it could decay faster or slower. So when you read in books and scientists use a radioactivity dating, be very careful with it, because more than likely it's not going to be an accurate dating of the past. Thank you, and you enjoy your lesson.